Once again, welcome to the lecture number 10 of the deep learning course. This particular session, let me tell you, is going to be very, very important and very, very fundamental. Okay. And please focus on this and ask the relevant question whenever any kind of doubt that comes in your mind. Please ask all the relevant question that you come in your mind. So don't think anything that you are asking any absurd question. Nothing is absurd, and those things are actually very important. If I have some kind of problem I'm not able to explain, then only you are asking the question. So please be vocal and ask all the kind of question that comes in your mind. Okay, welcome once again. I'm in this particular session I'm going to talk about the delta training rule and importance of the activation function. And let me tell you that many of the time that you would be asked these kind of questions from this particular lecture. All right, so few from the few last classes we were actually discussing that something like that if let's assume that there is some category of the items are here and some category of items over here, and if you want to do the classification, then you can draw a line on that. Here our assumption was that the data was linearly separable. So we can say that you can draw a line on that. If you can draw a line, it is going to be something, for example, 2x1 minus 3x2 minus 25 is equal to 0. If this is a line, so I may be totally absurd, wrong, but this is a line. Then we were talking about that we can design a perceptron where we say that minus 25 and 2 and 3 minus 3 and x1 and x2, and there is a summation. After that there is thresholding, and you can find out what is the value over there. So in this kind of setting, what we from where we started from the idea that since you don't know that what is the value of w, so you randomly initialize these value with something, and then you systematically modify these values. We have seen that there was a method by which we can apply, and we actually keep track that how many points there are error. Okay, so initially maybe error was on the 20 point, then it becomes 10 point, then it becomes 15 point, then it becomes 9 point, then it becomes 17 point, so that it is fluctuating like anything. Okay, it could be fluctuating like anything. But since we know my data is linearly separable, if we know my data is linearly separable, we know that at the end it is going to be 0. So even if there is a fluctuation, I don't care. I keep updating the thing. I keep updating the thing. We have seen that there was a proof that we have done in the last class, that after a few class back, that after doing something, it is going to hit the 0. And when this particular thing hits to 0, so the weight vectors corresponding to that particular scenario, I am going to utilize as a classifier. Make sense? So this is in this scenario we are currently right now in this particular scenario, but you know that this is not the real life scenario. Your data is not going to be like this. Your data would be like this, that there would be some positive example here, some negative examples here. So there would be some kind of overlap. So if there is an overlap, then what would happen if you just see this particular thing? Can I draw like this? That the number of error is going to be up and down, up and down. You know that at the end, what would be is going to happen? You know that whatever best you do, 3 points are anyway going to be misclassified. So minimum error is going to be 3. But do you know that minimum error is going to be 3? If you don't know, though, sometime when the error was actually 7, and after that it becomes 15, after that it becomes 9. So after some time, when it's again come back to 7, you would be happy that you should stop at that particular point. Ultimately, my point is this, that it is very difficult to tell that at what point you should stop, because your error is fluctuating. You don't know. And every time you don't know about the data, that what is the how many points are ultimately going to be misclassified, you don't know this thing. And anyway, all these things need to be we should program in such a way so that they should be automated. We should not tell that in what way the things are going to be. You only provide the data, and you devise the model, and your model should itself should find out the right parameter for that. No? You should not tell that if the number of error is 3, then I would stop. So where the system should stop? Because 0 is not anyway going to come. So how can you apply a stopping condition on that? It becomes very difficult. So this is a big problem. So uh, that's why training a perceptron becomes very difficult. Do you understand this thing? Training a perceptron becomes very difficult. You cannot train in this particular way because your data, your real life data is not going to be linearly separable. So what does it mean? Ultimately, I told you that whatever till now I have told you is actually waste, because you are not going to get the same kind of data on which you can apply this method. The method that we have studied, you cannot apply on this data, because real data, on the real data, you cannot apply that. What I mentioned, that because the error is going up and down, so you don't know that where to stop. So you cannot apply that particular method. So whatever we have studied till now is actually gone waste. Do you agree with me? We are into the big problem, because my system, if I want to apply, because real life data is not going to be like this, you cannot apply these things on the real life data. How many of you agree with me? Does anyone agree with me? Yes. Yes, you cannot apply this method because real life data is not like that. So if there is, if the things is coming up, error is coming up and down, where should you stop? So if you ultimately, if you want to find out the best system, then you cannot deploy this method. Okay, there comes another method that is called the delta rule to rescue us. So we are going to see a different kind of perceptron training system that is going to call, that we are going to call as a delta training rule. This particular method uses something very important that is called the gradient descent. What is the gradient descent? Gradient descent is very simple. We have talked earlier also that if, let's assume that there is a function, and let's assume that it is a convex function. Why I am telling convex function? Because I want to find out the optimization. No? Because if it is not convex, then how can there, I can tell that there is an optimization. Let's assume that the optimization exists. So if you want to find out the right parameter that is with respect to this, and you don't know, so just see that whatever your value is, you just see that what is the gradient at this particular point. If the gradient is positive, means what? If the gradient is positive, for example, if you are here, your gradient would be this tan theta is going to be positive. If you are here, your angle is going to be negative, and therefore this here your gradient would be negative. So if your gradient is positive, means what? If you go into, if you increase your weight, you are going to be further bad, because you want to reduce the thing, but your gradient is positive. If you keep going into the same direction, your things are going to be problematic. So you go into the reverse direction of your gradient. So this is what it is. You say that weights you can update by finding out that what is the gradient of the function with respect to that particular weight, and go into the negative direction of that particular thing. Apply with some kind of learning factor, and then you can update into this particular way. So if we can use a gradient descent, it would be a nice idea, because if you can apply the gradient descent, what is going to happen, that because you have defined the problem in this particular way, so can the error increase? Answer is yes or no. Can the error increase if you apply this kind of learning mechanism? Whether the can the error increase? Yes or no?
No, sir.
Error cannot increase, because you have taken you have taken the step with respect to the gradient, so error cannot increase. So if you can apply the gradient descent, what is going to happen? The error is going to be something like this. Let me plot it. So error is going to be something like this, that your error is going to be like this. So we want to apply a gradient descent. Make sense? Okay. One more thing that I wanted to do, I wanted to tell that earlier what was happening. Let's assume that the two classes are 0 and 1, and for some input, let's assume that the target is 0. Okay, target is 0. So you actually you have on your perceptron, you after the summation you have applied a thresholding. You got what value you got here? Let's assume that you got 0.6. Okay, your output is, let's assume that your output is 0.6. So because of thresholding, it becomes what? 1. And you, I'm sorry, let me just write it 0.4. Okay, if your output is 0.4, because of thresholding it becomes 0. Okay, so you become correct. But is it a right thing? Let's assume that there is some other item. and you are expecting the output to be 1, and your system is going to give it 0.554. Because of thresholding, it becomes what? 1, and you becomes correct. Is it a right thing? No. What should be this value? This value should be very high actually. If you want 1 at this particular place, this value should be 0.93 something. This value should be 0.12 some kind of thing. Ultimately, means ideally it should be 0. Ideally it should be 1. But even if it is not like that, do you want a better system? The better system would be such that where this value is very large and this value is going to be very small. A better system would be where this particular value, when your system want the output to be 0, the output of your neurons should be very small. When you want 1, output of your neurons should be very large. Then it is a better system. Okay. So what we say, why we got from this 0.4 to 0 and 0.54 to 1? Because of this thresholding. So if I remove this particular thresholding, once again, if I remove this particular thresholding and I say that no, I would use the exact value that is coming out to be here. So will it be the good idea? Will it be the good idea? Because what would happen, then I am forcing the system, then by this I am forcing the system that at the time when I am expecting the value 0, it should be very near to the 0. When I am expecting the value to be 1, it should be very near to the value 1. Okay. So one more change that I am going to do. I am going to tell that in that output that I have given the input x, the output is going to be the w multiplied by x. Earlier it was thresholding of the w transpose x. Okay, it was thresholding, but I am telling that no, I would not apply the thresholding. What is the effect of removing the thresholding from here? System try to be into that particular state that when I want the value to be 0, it should be very near to the 0. Output should be very near to the 0. When the value should be 1, it should be very near to the 1. Okay. So if ultimately what we want, that target minus output should be very near to the each other. So target minus output square, if I find out for all the items, all the data items on the all the data item, this value should be very small. Ultimately I want this, that if my system, because what is the output is that I'm going to find out over here for every x inside the database, I find out that what is the this particular value. I can say that this is an error and I want to minimize this particular quantity. Any problem on that? So now I am going to define the problem into a different way. I'm going to tell that the perceptron that I was using earlier, I am removing its thresholding. Okay, I am removing its thresholding and I am going to train using this particular problem formulation when I am going to tell that error is going to be represented by this particular quantity. It is again going to tell me the how bad my system is, because if the difference is high, means that on most of the item it is not going to give me the same thing. You may be asking, sir, why there is half? So half is just a constant parameter. You know that. Let's assume that I have an array where some value is there 3, 5, 9, 8, 2, 8, 18, and let's assume that it is the first item, second item, third item, fourth item, fifth item, sixth item, and I want to find out that on what particular value the minimum is there. So can you tell me on what particular index the minimum is there? It is on 5. Am I right? So if I say that minimize, a, or if I say minimize 2a, or if I see that minimize of half of a, so will I get the same answer or a different answer? If I want to find out that minimize for what quantity it is going to be minimum. So if you want to minimize this quantity, instead of this quantity, if you minimize half of that quantity, it is also going to be the same, going to have the same effect. Make sense? Because 2a is what? 6, 10, 18, 16, 4 and 36. Again the minimum is here only. Half of a means 3 by 2, 5 by 2, 9 by 2, 4, 1 and 9. Again the minimum is here. So by multiplying factor, it is not going to have any adverse effect. However, we would see later that because of this some mathematical convenience we obtain, so we are going to see later. Once again, we have a database. On that database, we want to find out the right parameters of W's, and I am going to define the system in such a way so that if you are going to pick any particular item of this, you multiply with the weight and then you find out that what is the output and your output. And since for every data item there is a specified target output, the difference between target and the output given by your system, I am going to call it error, and my objective would be to minimize this particular quantity. When you define the function in this particular way, what is going to happen that that your error is going to be a continuous function. Okay, so and if you use gradient descent to go ahead, because you can, if you apply gradient descent on this particular formula, so every time your error is going to reduce. So if every time you're going to error is going to reduce, then you can by yourself think, please focus on this particular thing. Let's assume that this is how the error is reducing. You can see that initially the error is reducing very fast, but after some time error is not reducing that fast. So you can find out a point that you can say that is the elbow point. So you may stop at this particular moment, and you can say that after that not much improvement I'm going to achieve, so I can stop at this particular, safely stop at this particular place. Once again, if you define the error function into this particular way, how can you modify the weight? Oh, wi, if you want to modify, you say that you go into the negative direction of what? There is some eta, that you find out that what is the derivative of this particular thing, and with respect to that particular weight. Okay, this is how you can modify your weights. And if you modify your weight using this particular formula, your error is definitely going to reduce. Makes sense? Your error is definitely going to reduce. This is what the formula is. Any questions on that? If you have any confusion, please let me know. Okay, what is this quantity? What is this quantity? Let us try to see that. If you apply a because you know that what is this particular equation, it is a w0 x0 plus w1 x1 plus w2 x2 dot 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 wi xi plus dot dot dot, this kind of equation you have. And if we want to find out the derivative, so there are multiple data points. Okay, for every data point this particular equation is there. So just focus on any particular data point, and therefore then we can remove this particular summation term, and we can see this particular inside thing. It is if you want to find out what is the derivative, let me find out what is the derivative of EW with respect to WI. It is going to be the derivative of you have to find out the derivative of this quantity. It is half multiplied by summation term. You can right now don't neglect it, let it be there, because if multiple terms are there, you can think in this particular there are multiple terms. Okay, if there are multiple terms and you want to find out the derivative, so you know that the derivative can go inside and you can find out the derivative of individual term. So you can say that for all d inside the d, it is a derivative of dwi with respect to td minus od. Okay, square. TD minus OD square, if I ask you that what is the derivative of this particular quantity, you can tell me that, sir, it is going to be 2 multiplied by TD minus OD and del upon del WI of OD. This is what equation is. And that's why I have written the 2 over here, sigmoid of D belong to D and half, so that at some point of time I can take this advantage and remove this kind of 1 and half. So what we have summation of all the D inside the D, TD minus OD, and then this particular derivative term. Okay, so let us find out that what is the derivative term. What is OD? You know that OD is this. OD is this. Okay, OD is this equation. So if you find out the derivative of this particular quantity with respect to the x wi, so wi is only here. All other places actually there is no wi, so they becomes a constant with respect to wi, so they become 0, and only this term suffice. You have to find out the derivative of this particular term. So this is also constant with respect to that, so only derivative of wi with respect to wi becomes 1. So what remains? Xi. So I think I missed this minus sign because minus OD. Okay, this was the minus OD. So minus of xi remains over here. Minus of xi remains over here. This is what the derivative. So you can put this thing into this eta time this particular quantity. So let me clear the clutter and give you this particular idea that this is how we can write this particular equation. once again, if I, from very high level perspective, if I wanted to tell that if this is what the function is, then you find out the derivative of this particular function with respect to every w, and then all the w's can be updated using this particular weight formula. The same thing that you use this particular formula, find out what is the derivative, and then you update your derivative in this kind of formulation, which is going to be, a few minutes back we have seen that this is what it comes out to be. Make sense? All right. So let us let us see the algorithm. Initialize the w's with the random weights, and for all the data items, you are going to find out what, that if you want to find out the update, you want to update the value of wi, it is going to be wi plus something that we are going to add, and this addition term is going to come from where? Target minus output into xi eta time. This is, you are going to find out the, what the summation is, and after this summation, you are going to add over here, because it was a negative becomes positive, na, wi, because this is a negative term, na. There was a, everywhere xi was actually multiplied by -1, so and you are initially the value was 0, so ultimately it is going to be a negative term, so therefore it is positive. I think I have missed, I think no, eta is actually every time multiplied, so this is fine, this equation is fine. The same thing, you can see that same thing being explained over here. So this is what the formula is, gradient descent. This is how you apply the gradient descent into the system. We have done a new formulation of the problem, and this is called the delta rule. Okay. We know that the data is multidimensional, means there are different x1 x2 different attributes, and with every attribute target value is also being specified. This algorithm converges toward the minimum error hypothesis. This is guaranteed because we have seen why it is going to happen, because we have seen that gradient descent has this kind of property. So this is a very interesting kind of approach. However, there is a direct method of applying all these things. So, and I think few lectures back we were actually discussing on that, that if you directly apply these kind of optimization methods, you will not be able to find out the solution, because number of multiplication is going to be too much. However, I'm talking about right now on this delta rule, and by this you would be able to find out the solution. So are you happy? Yes or no? Why I want you to be happy? Because earlier we have seen that on the my database, if the database is linearly separable, then only I can find out the solution. But now we have find out a system, we have done a new kind of formulation. By using this kind of formulation, even if the data is not linearly separable, we can go to the minimum error hypothesis. We can approach to the minimum error hypothesis. Are you happy on that? Good solution, delta training rule?
So
Yes or
will
no?
this convergence depend upon the error function that we have defined? Like will it reduce or not?
Look, why would you define any other error function? This is actually you want, na? So this is going to be your error function. Why you would define any other error function?
Like some other function that we want to minimize? Yeah.
Why?
Yeah.
Because you want to be near to the target only. So that's why we are defining this. What this
Oh,
particular function says, that you want to be very near to the target. Your output should be very near to the target.
yes, sir.
Okay. This is the
Hmm.
real function. There. However, you can tell that instead of a square, you are going to put the cube or any other thing. So those things actually comes into the different kind of thing. But already we actually discussed that this function should be only requirement is this, that any kind of function that is convex function actually solves our purpose. You come up
Oh,
with this thing, so that when TD and OD are actually near, the value should be lower, and this function need to be convex. That's it.
okay, sir. Got it. Thank you.
So it gives you a kind of solution that actually satisfied all your problems. So you must be happy that now you can train the perceptron, that on the real data also you can train it. Make sense? Okay. So if you can train it, you would be excited to have more power, because we have seen earlier that if you put multiple neurons into the multiple layers, what is going to happen? So we have seen that the different kind of places you can do a different kind of if there are multiple places where there are data is scattered, so multiple linear decision boundaries, then you are combining them and you can come out of that. So you can push more power to your system by having a neural network. Make sense? So same kind of system you can apply, and you can tell that I am going to develop the, if you want more power, then you can apply what? Then you can apply what? If you want more power, then you can apply neural networks. Agree? Yes or no? So, Utkarsh, Rohit, Akshit.
Yes.
So, so one thing I have seen this, na, if multiple, uh, if uh, if you want to push more power to the system because your data may be complex, then you can put the neural networks. Make sense? All right. So here I have made a neural network. Hmm? And please note that the few minutes back, our system, our neural, our perceptron was this, that whatever input is going to be there, I'm going to find out their summation and going to give as an output. If you need output as 0, then it gives value that is very near to 0. If you need value output as 1, it gives the value that is very near to the 1. All right. So here there is a simple system. Please look very carefully. So this is the input layer. This is the output layer. There is one hidden layer. Okay. So here x1 and x2, two values are there that I'm going to provide. And this is one is the, as we told that, always tell that it is a slack input. So if there is a perceptron, so let's assume that it has a weight w1. This is the first one. Okay, I say that this is the first one. So 1 0 1 1 1 2 2 0 2 1 2 2. These are the weights associated with this. Everybody, do you understand this? Abhijit says, sir, you said that we avoid thresholding. However, sigmoid is used in neural network, which is thresholding. Am I right? Abhijit sir, you are perfectly right. So let us wait for a few minutes. All these things would come with more detail. Okay. So I'm just talking about what we have talked right now. So we are into the happy mind state right now. So we just try to see that how happy we are right now. So that's why this particular example is, let us say, evaluate. Yeah. So everybody tell me that if this is the perceptron 1, this is the perceptron 2, and this is the 202122. Similarly, this is a perceptron 3, so 303133. So what is the output? Can you tell me that what is the output? This output is going to be W30 multiplied by this 1 plus W31 multiplied by what? Whatever output that you are going to receive over here, W1 transpose into X plus W32 plus W32 into whatever output you are going to obtain over here, yani W2 transpose of X. Am I right? Can you write yes or no?
Yes, sir.
Okay, so let me go much deeper and find out that what is this particular value, because I wanted to find out this value. This value is going to be W10 multiplied by 1 plus W11 multiplied by what? X1 plus W12 multiplied by X2. Similarly, what is this value? This is W20 plus W21 multiplied by X1 plus W22 multiplied by X2. Can I write like this?
Yes,
Okay.
sir.
So I can replace this value with this more generalized format. So why not you multiply this value inside? So you can say that here W31 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 is multiplied, and here W32 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 is multiplied. So I can remove these parts. Okay, they are multiplied. Okay, you understand this, and there is W30 is some term. So this multiplied by 1, this is multiplied by 1, so I can put them into one place. And since there is a parameter that is a x1, and here also there is a x1, so there is some multiplication, and then I can say that that value may be, I can say that a multiplied by x1. I don't know that what is the multiplication of this quantity and this quantity. Similarly, I can combine with the x2. I can say that b multiplied by x2, and all these quantity I can say c maybe. Can I write like this?
Yes, sir.
Yes. Okay. So what is the output that I got? I got something that a multiplied by x1 plus b multiplied by x2 plus c. So this output I can get from, for example, there is a single perceptron, and where c, a, b, x1, x2, if this is a single perceptron, I can get the same output of this also. So I have created a neural network, but ultimately what happens, that it has actually collapsed to this particular system. So the same thing is being shown over here. that the output is actually you computed in this way, ultimately to reach to this particular value, okay, with a different kind of values. So ultimately your expression is actually that you finally got the expression, it is a expression of the single perceptron. So this neural network that actually you have created actually converges to a single neural network where different weights are there only, okay. Oh my god, what does it mean? That whatever big neural network circuit you can make using this kind of perceptron, where there is no, please note, there is no thresholding. If there is no thresholding, it ultimately means what? The network collapses and it only represents a single decision boundary and single perceptron. Okay, so it actually collapses. So big problem. So one side I was able to go to the minimum error, but if when I combine them, they becomes a single perceptron. It's a big problem. Do you understand this? How many of you do agree with me? Again, there is a problem. Why it is happening? Because I am not applying any kind of thresholding, any kind of activation over here. If I had put any kind of activation, once again, please focus on this. If I had made any kind of activation, for example, if here in this particular equation, if I had put any kind of activations over here, then you cannot simply expand this particular quantity and tell that W3 is multiplied and there is a summation possible. So all these things happening because I have not put any kind of activations over here. What kind of activation I want, what kind of activation I want. So there is a question that why single perceptron is a problem. The problem is this, that is the problem. Let's assume that the underlying question that is given to me is a complex question. To solve that particular problem, I need more power to be pushed into the circuit. Now I cannot push more power because even if I push more power to my circuit, it becomes a single one only. Okay, so I am limited in terms of my power. Only I can create a linear decision boundary. Okay, so this is the issue. That issue is this, that why I have not done any kind of thresholding. So what I wanted earlier, what was the issue? Issue was this, that there was a thresholding. So suddenly from 0 to 1 things were actually going on. All the intermediate values were not there. So what if I apply something so that instead of instead of going only giving 0 and 1, it gives all the values down the range. If I apply any kind of function over here, if I apply any kind of function on this particular thing, that is actually monotonous kind of function, any kind of function, not the linear function, any kind of other function I can apply, then you cannot directly multiply, and then your system is going to preserve the network architecture in your equation. So I have done lot more good much. Do you understand this thing? How many of you agree that once again I was able to, this equation was actually became into this particular form only because there was no thresholding. If I apply a kind of if I apply any kind of activation function over here, then this cannot go inside and directly multiply, and then the equation would be complex and it would preserve those kind of things into the system. So this actually brings us some kind of requirement that there should be some some non-linear transformation on this thing. So they can we call it activation. So non-linear transformation can be applied on the output, and we call it activation. Very important thing I'm going to tell. Till now, in every slide, I was telling that I had the weighted multiplication, then I apply a thresholding, and it is a perceptron. But when I say that there is an activation, it is called neuron. Neural network that you actually talk about, they are actually combined using the neurons. So this is what the neuron is. We need a kind of activation. If we apply activation over here, then this function would not get collapsed, and we want these. Then the power of the architecture actually comes in into your system. All right, what kind of choices we have for this activation? So one very simple choice is this, that you can use the sigmoid, and sigmoid is a very simple kind of function that that sigmoid of x is defined upon 1 plus e to the power minus x. So instead of whatever value that you have here, you put this sigmoid of your function becomes 1 plus e to the power minus w transpose x. So you instead of using the w transpose x, you are going to put this function. So is it a simple function? telling that I am going to use a simple function. But is it a simple function? No.
No, sir, not really.
You may be thinking that, sir, what are you telling that I'm not using single? How come it is simple function? There could be any other function. But let me tell you that why we are using it. Okay, there are very subtle reasons that why we use it, because sigmoid function, the output of sigmoid function is between range of 0 and 1. Okay, so if the output is ultimately the output, whatever was coming, we wanted to use it for the classification. So here this output also we wanted into the range of 0 and 1, and this output is also going to be into the 0 and 1. So that is a good thing, because then we can utilize that whatever output is coming to me as a probability. Okay, this is the first thing. Second thing is this, that the derivative of, surprisingly, derivative of sigmoid of x is the sigmoid of x multiplied by 1 minus sigmoid of x. Okay, so because when you want to apply a kind of gradient descent, so you have to find out that what is the gradient at that particular point. Na? So gradient you can very easily compute that. If you know that what is the value of sigmoid function at that point, if you want to find out the sigmoid, immediately the sigmoid function, sigmoid is, gradient is also available. Okay, and non-linearity it provides, so that it becomes a very important, very good choice. So even if you come up with any other function, they are also going to have, ultimately going to have the same kind of effect. So this is the reason that we use the sigmoid. Once again, why we use sigmoid? Because its output is between 0 and 1, and therefore the output we can utilize as a probability. And finding out the derivative is also very easy. So when we want to train our system, so if we want to find out that what is the derivative, it is immediately available. You didn't have to do any kind of computation and different kind of thing. Sometimes the classification is into +1 and -1. In those cases, you can use another function that is called the tanh function, exp, and this is again defined by exp of x minus exp of minus x divided by exp x plus exp minus x. It gives you the output into the range of 0 and 1, and this is a better choice for the activation function into many of the cases when the two classes are -1 and +1. In both of these functions, there is a problem that when you actually reach to this particular point, you can see that your actually gradient actually decreases. You can see that the gradient is very high at this particular point, but gradient actually decreases when you actually saturate. At that time, the gradient is very less. So what happens that because you know that you weight updation required weight plus alpha time gradient of that particular quantity. The gradient is very small, means what? Your weights are not changing, they are changing very less. So this is a kind of problem that these particular function actually faces. So there are some notion that you can utilize. For example, another function is a softplus function. This is a very interesting function that says that log of 1 plus e to the power x. So you know that e to the power x and log are actually, they are enemies, so they actually kill each other. Ultimately this values comes to be 1 x only, and x means a single line. However, because adding of this particular one, so you know that I should not do like this, because 0 is here, so the line would go something like this. X is equal to 1, line goes like this. So it is like this. Because of adding of the 1, it becomes that into the negative places, it actually take cares, and it does not vanishes. So this is the only reason. So if you put the things like this, what happens that the gradient is going to be very high, because when this particular value is high, the gradient is actually very high, so learning is going to be very fast. However, this is a good idea, but again there is a problem that you know that log and e to the power x, all these things, if you want to compute, you have to do a lot of mathematical operations. So ultimately, when you are going to do the training, so lot of CPU cycles are utilized to actually only compute these things. So it would be better to come up with a bit simplified function. So next idea is to use rectifier ReLU, called the rectifier linear unit ReLU. It says that if the value is greater than 0, it is the x only, otherwise it is 0. So in this particular way, it is just, you can represent as a maximum of 0 and x. And again here also the gradient is very simple. If you want to find out the gradient, it is going to be 1 or 0. So very simplified function. So most of the time, if you want to do a fast learning, you have to apply the ReLU, and into the bigger network inside ReLU are actually most of the time they are placed. However, there is a problem. So the problem is called the dying ReLU problem. That tells, because you know that into the positive side, if you are here, you have the gradient. Otherwise, what is the gradient at this particular point? 0. So there is no gradient means what? If you are into this particular region, you are not learning. Again, this is a big problem. So into the negative side, one side you are actually not learning. So sometimes people say that instead of putting 0 at this particular place, you put 0.1 into x. Okay, so that you also do some kind of learning. So this equation, when you change it into this particular way, instead of 0 some fraction of the x, then this is called the leaky ReLU. This particular function is called the leaky ReLU. So we have seen a very interesting slide which actually tells that what is neuron, okay, and what are the different kind of activation function, and what is their importance, why we need the activation. It comes from this particular slide, because otherwise what would happen, everything would collapse. Okay. uh, we have seen that a single perceptron can only express the linear decision boundary. So when we want to build a neural network, it is going to give me a good kind of circuit. So we have seen that we have applied a kind of activation, maybe sigmoid activation, and using sigmoid activation, if we have developed a neural network circuit. So let's assume that there is a unit and that is connected to this thing, and there is a weight W. I want to find out what should be the next weight if W is there. So I can say that W is equal to W minus eta times what? Gradient. A gradient of what? You define that, what there is some loss function you define over here, and you find out derivative of that particular loss with respect to this W dW. In this way you can find out this. Back propagation in more detail would come very soon. Into the next class we are going to discuss about the back propagation. Again, it also applies the gradient descent, as we have discussed. Using gradient descent we can find out the same thing. However, into the general setting, we have seen that when there are a multi-class classification problem, when multiple classes are there. For example, there is this amnist database where 10 categories are there. So for example, it contains the digits. So digit could be 0, 1, 2, 3, 4 to 9, 10 things. So at the output layer, there could be there need to be 10 different there need to be 10 different neurons that are going to tell that what is the probability of being 1, what is the probability being 2. You feed a image over here, and this system tells that what the probability that the digit is 1, 2, 3, 4, 5, 6, like that. So in that case, if you want to define that what is the error function, first you have to find out the error with respect to all the outputs. So if there is instead of only having the single summation term, you introduce one more summation term, and for all the data item you are also going to find out that what is the error with respect to every outputs, how many outputs are there. So sometimes you need to modify this function into to be more general. And the back propagation algorithm is this. We would come back to this into the more detail. I just wanted to give you the focus on this particular thing, that very simple thing, that what I wanted to do, I wanted to update the weight. How can I update the weight? Take the previous one and add something. What I need to add, eta time something, and that something is being computed using this particular formula, and that is different from the output unit and hidden unit. And how these formula is coming, you talk into the next class. Okay, we'll talk much into the next class about the what is the uh, back propagation and how it works. So before closing this session, I want to give you a small understanding of the neural network that would be needed, a small convention, and the understanding of the neural network that would be needed to understand the back propagation. So now our focus is going to be that if there is a connection and there is a weight W, how can we find out the right weight for this particular thing? Because multiple weights are there, so many weights are there. How can we find out the right weight for that? As I told you, we are going to use an algorithm that is called the back propagation. So in this particular setting, so can you tell me something? This is the input unit, this is the output unit. Okay, in output unit and input unit, there are various neurons applied over there. So first thing that I wanted to tell, every neuron has a number. First neuron, second neuron, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, and 13th neuron. You first provide them a name. This is the input layer, this is the output layer, this is the input layer, this is the output layers, and this is the hidden layer 1, this is the hidden layer 2. This is for the nomenclature people actually use. Okay, so if I ask you that 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 you know that there are some input also, na? So if I just focus on this ninth one, so how many inputs it have? Coming from 4, 5, 6, and 7. So they are actually talked as that this is the first input, this is the second input, this is the third input, this is the fourth input. Okay, okay. So there would be a weight associated. So I say that W91, W92, W93, W94. Okay, everybody can see this. Yes or no? Do you understand?
Yes,
Do you
sir.
Yes,
understand?
sir.
Yes. Okay. If you
Yes, sir.
understand, so can you tell me that what is this particular weight?
W62.
6 2.
W62. Correct. Very happy to listen this. So you forget about this from where it is coming. It is coming from 2. You don't remember that. You see this that what is coming from here. Okay. So similarly, x62. What is x62? What is the x? What is the input that is coming from that particular direction? Okay. All right. So if since it is a since it is a neuron, so it is going to give you some output. So what is the output at this particular place? Uh, so let me show you once again this slide. Okay, here xij represent ith input to jth unit. So I was telling this particular thing. This red one, can you tell me what is this? It is 9 4. Okay, x9 x94, because to the ninth it is the fourth input, x94. W94 is the weight associated. Net j, what is net j? Net j is net j is means net j is actually what is the net of 9. Net 9 means you know that W91 x91, W92 x92 plus W9 W93x93, what I'm writing, x93 plus W94x94. This is how this equation is called net. Net 9 means what is the output of 9. So if you understand this, can you tell me what is the net 6? Net 6 is with respect to all these input. Net 6 is all with respect to this. So it is W6, W61, W62, W63, and then you multiply with x respected x with that. So net, you understand? Yes or no?
Yes,
Net.
sir.
Okay. So if I want to find out that what is the output of 9, can you tell me what is the output of 9? Output of 9, it is going to be the sigmoid only. Let's assume that sigmoid is placed over here. Sigmoid of net 9.
Sigmoid of
This is the
net.
okay. Okay, very good. If you want to find out that what is the output of a particular unit, it is going to be sigmoid on that particular net. Net is actually multiplication of all these W's. This is how you find out this. TI is also very important thing, that you know that if some output is coming for this, it is O9. But what should be the output? I don't know. Sometime, for example, at least for the output units, I know that what is the target T12, what is the target 13. This would be with respect to every input. Okay, what is the target? If we specify an input with respect to that, what is the target of that particular value, it would be given to me. Okay, target mean what should be the right value. Okay, so ultimately our objective would be that t t o t of a particular tj 1 minute, tj minus oj should be very small. So we want to minimize this particular quantity. We are seeing for many times. There is another set that is called the outputs, and this sets means that which are the unit they are there into the final layer. So, okay, so this is the final layer, which are the unit 12 and 13. So this is the set called 12 and 13. And similarly, there is a down there is another set called the downstream of j. Downstream of j are those, for example, let me write D downstream of 9 is a set that contains those things which are getting output of this 9. So who is taking the output of 9? They are 12 and 13. So if I ask what is the downstream of 6, so they are 8, 8, 9, 10 and 11. Am I right? On the 6, 8, 9, 10 and 11, they are taking output.
Yes, sir.
Yes. So we are interested in finding out the ED divided by WJI. What is WJI? Because look, let me tell you, this is, I am going to simplify your problem. If you want to find out, for example, what is the weight of, so this weight is, we have talked about W94. If you want to find out W94, so error that you have defined over here, that was the summation of all the, with respect to all the data point, and summation of with respect to all the units that were there. You target minus output square, you want to find out the derivative of this particular quantity with respect to this particular, with respect to this particular weight, derivative of this quantity with respect to this particular weight. And then if you find out this, then you can modify the weight by saying that W94 is equal to W94 minus eta time del E d upon del WJI. This is how we are going to do. Any questions on that? Correct? Yes? Are you with me?
Yes, sir.
Yes, sir.
Great. So if you are with me, so we want to find out this thing, and I don't want to go into the much mathematical detail. Into the next class, we would go and explore it more. Actually, it is nothing but you can say that ED upon net j, and then because of the chain rule, you can say that ED upon net j, then net j upon WJI, and then you can see and net j upon WJI, you know that it is XJI. I would go into the detail into the next class. And this thing we have few minutes back shown actually when I started lecture. Na? Net j is a multiplication of these weights and xi. If you find out the derivative with the xji only, WJI only xji term would remain. So it is going to be xji. So ultimately we want to find out this particular value. How to find out this with respect to the sigmoid functions we are going to see into the next class. Thank you.